Christer Weinigel, who will speak about NTS and the deployment and usage. Welcome, Christer.
Where does he work?
Thank you.
He works at Netnod.
So, last talk of the day, so I hope you're still awake. Well, let's see if I can make this one work, because I always mess up. So, my name is Christer Weinigel. I work for Netnod, and I've done that for, 3 years or something like that by now, or maybe 4. So, and yeah, let's talk a bit about NTS and usage of NTS. So, let's back up a bit to start with NTP. NTP is basically the protocol for time distribution over the public internet. It's been around for a long time. It was created back in 1980 by David Mills and was sort of almost an internet standard in RFC 958, and that's one is from 1985. And I think he had proto versions of NTP already in 1980. The latest version of NTP is version 4, RFC 5905 from 2010, so it's getting a bit long in the tooth also. It has very good timing accuracy, and with good I mean millisecond over the public internet, so we're not talking nanoseconds here, but for something that's routed over a public network is really good. There are multiple implementations. There's the NTP reference implementation, there's the NTP sec crony. They're stable, they've been around for a long time, and they do a really good job. And, well, I could almost skip the slide because everybody has been talking about this. And you've seen the same picture of our rack at least 3 times now. So basically, we have multiple nodes. They all have redundant hardware. And the interesting part for me, really, since that's what I've been working on, is that Netnod has a NTP implementation running in FPGA. And the reason for that is that basically we want to be able to survive a denial of service attack. So we have the networking bandwidth at Netnod to handle quite a lot of traffic. And each FPGA that handles NTP here can do 4 times 10 gigabit at wire speed. So we can, I don't know how many, what's that? It's 1,000 bits per packet, so we can handle about 10 million packets per second of NTP traffic on one port. And then we have 4 ports on each FPGA. And since everything is redundant, we have 2 FPGAs at each node. So we can do NTP almost as fast as you want to. As the previous talk said, we do have traceability to UTC-SP, and via UTC-SP we can trace our time back to UTC, the paper product, and also to other timescales, such as sort of UTC, USNO in the United States. Here's our nodes, 6 different nodes in 5 different locations. We have 2 nodes in Stockholm. So, what are the issues with NTP then? Why do we need something else? Well, there's basically no security in NTP. It's a plain text protocol. It's only 48 bytes with 3 different timestamps. And all of this is plain text, so it's vulnerable to a man-in-the-middle attack. If somebody owns the router you connect through, they can modify the packets and they can make you believe that the time is different from what it actually is. And that's not really good because time is important. Lots of security sensitive protocols, TLS, they need time to be able to validate certificates. And TLS is used for HTTPS, the web protocol. It's used for SMTPS. Almost most protocols you find on the internet today, they are based on TLS. There's also DNSSEC, which also needs accurate time. And I mean, OpenVPN uses TLS in the end, so it can be a bit of a problem. And I'm also lying a bit when I say no security. There is actually a bit of security in NTP. There is something called authenticated NTP, where you basically do MD5 or SHA-1 hash of a packet together with a shared secret. And this works decently, except that the crypto algorithms we're using, they're getting also kind of long in the tooth. MD5 is basically cracked by now. SHA-1 is, there are practical attacks on SHA-1, I believe. The most troublesome issue with authenticated NTP, though, is that you have a shared secret and you have a key distribution problem. You can only have up to 65,000 keys because there are only 16 bits in the key ID. And how do you get these keys to people? Today, people who do authenticated NTP, they basically manually somehow distribute the keys. You put them on a USB key, USB memory, ship them to somebody, or you send them with PGP encrypted mail. But it's troublesome. It takes a lot of manual work, so it doesn't scale to internet sizes of 10,000s of clients or 100,000 clients. There was also a protocol called AutoKey for NTP, and it never caught on. It had weaknesses in the encryption. It had too short keys, and so it never caught on it, and it hasn't really been used in practice. So then we get to NTS coming to the rescue. So what is NTS? Well, it's basically NTP with security, or NTP with scalable security. It adds encryption and authentication to NTP. It scales to basically an unlimited number of clients. It was a sort of NTS was an ITF draft for years, and it had kind of stalled. And then my colleagues at Netnod got involved during 2018. Marcus Dansaria got involved, and also a lot of other people got involved. So during 2018, things started happening with the NTS. So actually, I got involved in 2019 when I started working for Netnod. And finally, NTS was published as RFC 8915 in September 2020. So it's basically an internet standard right now. So just to dive down a bit into the technical things about NTS, it's basically two phases. The first phase is key establishment, NTS KE. So we're using TLS with the same infrastructure as you use for HTTPS. So basically, we have the same kind of certificates. You can get a certificate using Let's Encrypt. You connect over TLS to the server, and the server will create a session key, almost the same as the shared secret for authentication in authenticated NTP. The secret is stored in something called the cookie, encrypted in a way so that only the server can get the data out again, and the server hands over the cookie to the client, and then the server promptly forgets all about that client. The client then comes back, and then we have the second phase, which is timestamping. I call it NTS-TS in a lot of documents for NTS timestamping, but that's not an official abbreviation. It doesn't say NTS-TS in any of the RFCs. But it's basically NTP, or in the RFC it says NTP because it is NTP. And what the client does is to say, okay, I make an NTP request, I add an extension field with a cookie. And the server gets the cookie, extracts the shared secret between the client and server from the cookie. It takes this one, authenticates, signs the response with this shared secret, and then throws away the cookie again and sends the response back to the client. So this means that the way this scales is that, well, we basically do authenticate the NTP, but the secret is always stored by the client. The server doesn't have to know about it, and this way it can scale to millions or billions of clients if we want to. So that means that this is scalable and can be used by anyone. Then we get to NTS implementations, and I've been attending the ITF hackathons working on NTS. And basically, the first implementation was in C++ by a guy called Martin Langer in Germany. He did a C++ implementation for Windows. Somebody has done C or there are multiple people who have done C implementations. There's an implementation Go done by one of my former colleagues, Mikael Karel. There's a Python implementation that I did during the ITF hackathons, and there's also an implementation in Rust. The two big NTP servers on Linux, and usually an NTP server is usually both a server and a client. So the two big NTP servers on Linux, NTP-SIG and Crony, both of those support NTS by now, and the maintainers of those projects have been actively involved in working on NTS. And if you run a modern Linux distribution, such as Debian Bullseye, Ubuntu 22, I believe, Fedora latest, you have NTS-capable NTP clients. So that's quite good. So it's easy to get started with NTS actually nowadays. And of course, we at Netnod, we do NTS. So we have our own custom NTSK server based on my Python code. We have a custom NTST implementation, and since we did NTP in an FPGA, of course we do NTS in FPGA also. So that one can do 10 gigabits at wire speed. NTS is more complicated than NTP, so we can't do 4 times 10 gigabit, but we do at least 10 gigabit on an FPGA. And this is not the end, but this looks like the end. If you want to read more, here are a bunch of references. We have white papers about NTS, why it's important, the principles behind it, deep dive into the details of the key exchange. We have a white paper about our hardware implementation in an FPGA, the links to the RFC best practice for connecting to NTP servers, and most of what that document says is actually true for NTS servers also, since NTS is basically NTP. And of course, a list of our time servers. And I don't know if we've said it that clearly, but we have 6 public NTP servers. They're open for anybody to use wherever you are in the world. And so far, we have enough bandwidth to handle it. Almost. I'll get to that, actually. So, time for a little movie. And let's hope this works, because nobody else has tried to show a movie at one of these conferences yet. So this is sort of a map of NTS usage, NTS-KE usage, which has been geolocated. And the white dots, our servers are in Stockholm, and the white dots, those are sort of my clients where I do testing against our servers. So they show up really clearly in the beginning here. And this is when we sort of switched over to our new NTS servers. And you can see, well, not that much, 1,000, 2,000 hits per second, maybe. And this is going to be the most boring movie in the world if we run it at this rate, because nothing really happens. So these are just sort of enthusiasts using NTS. It's people who have been working on the standards, people who just want to try it out. So come on, I'm talking too fast. Sorry about that, because it's a few seconds left. So speed it up. And as you can see, nothing happens. You can see that there are people using NTS. There's a client. My clients still show up a lot because I do testing all the time to verify the service is up, and then people connect to it every now and then. So there are a dot in Australia and quite a lot of users in Europe, actually, for some reason. And this is how it looks for another 8 months until October. So end of October, it starts to increase a bit. Now we're about 2,000, maybe 3,000. Coincidentally, ITF, the last ITF started on 7 November, and this is where things start to happen. We're up to 5,000, and then a few days later, we're up to, I think on the 7th, I believe we reached 10,000. So somebody's starting to use NTS, and it's starting to show up on the map. And one little interesting thing here is, or let's wait a second, but you can see it's increasing. Now we're up to 80,000, 100,000. So a week later, we were up to 100,000 hits. And I looked at this and, yeah, no problem. Our servers can handle this. It doesn't really matter. If you look at this, you can actually see how the glow is moving around the globe. And the interesting thing is, if you pause this at 12 o'clock, you'll see that 12 o'clock CET, you'll see that it's the brightest during noon. So for some reason, the usage follows the daylight. I don't know why, but that's sort of how it is. And it just keeps increasing, 250,000. And I'm sort of, okay, no problem, we still handle this. And a few days go by, Christmas comes, I go on Christmas vacation just like everybody else, and the numbers keep rising. And for you who talk about gigabits, this is nothing. I mean, 100,000 hits per hour, what's that? That's a quarter. That's 250 hits per, no, that's 25 hits per second. That's nothing at all. So we could handle this with a single server, tiny, small machine that we ran this on. And I've been known to sit in meetings and say, well, I'm not worried about load. Nobody's going to use this. It's just enthusiast for now. Except that it kept on increasing and increasing. And I think I got back to work a week into January, and then we were suddenly seeing problems. My poor little server was overloaded. The Linux kernel started spewing errors about running out of buffers. You're probably under a denial service attack. Small problems. So we solved this in the beginning by just saying, well, we'll just give more CPU to the system. So we added more CPU, more memory, and that solved it for a little while. And then the usage kept increasing. So this is when I'm starting to get a bit panicked, because now we're up to 1 million hits per hour. And I'm sort of, okay, CPU pegged. Logging is starting to become a problem, because we're logging every request, and that the loggings turn out to be a single thread, so it doesn't. Even if we add more CPUs, we can't do the logging at rate 1, 2. So I had to turn down the logging a lot, and work on my code, because there were timeouts and things like that that were too long, so stale connections kept using up memory. And this is what we ended up with on the 27th of January, 2 million hits per hour. So, I mean, we can scale this up, but it turned out to be a bit of a problem for us, and panicky for me. So let's continue with this, not the movie. But so, as I said, actions. What did we do? Well, we threw more hardware to problem, more CPU, more memory, make the timeouts shorter so that idle connection or dead connections don't use up memory, reduce logging. I had to improve the threading in my code, had to do some kernel optimization. For example, we didn't do interrupt affinity properly. We only used one CPU to handle interrupts, so we had to change the kernel settings so we spread the interrupts. I mean, if you do a busy web server, it's the same kind of work. And next step was to actually start to do load balancing with the node. So we said, okay, we're hitting bottlenecks from a single thread, so we'll just add more machines. So we added 2 machines, and one of my colleagues set up load balancing at the IP level before it, and that basically means that now we can scale up as much as we want to, because adding more machines is easy. Another thing we did was to add more nodes. So our first nodes were just in Stockholm, and we were planning to add Gothenburg, Malmö, and Sundsvall during February, but my poor colleagues had to scramble and do that a bit faster or earlier than we had planned to. So we actually have all of those sites up right now. So now you can do NTS to 4 out of our 5 locations in Sweden. And Luleå, I've been promised, will be up within the next few weeks. So basically, Luleå is far away in the north. So it will take. We're not planning a trip until I think next week or the week after. Next thing, conclusions. Well, I did have to eat my own words, as I said. I said nobody will use NTS. I was wrong, and I'm actually personally quite happy about it. For me, I've never had a service be this popular before, and it's quite fun personally to see that, well, somebody's actually using something I've done. I also feel that NTS is good for the internet. It increases robustness, it increases sort of security, and in my small way, I've made a bit of a difference and made things better. So that makes me quite happy. Well, as you have a Q&A, but if you have any questions in the future, if we forgot something, well, this is me. Please mail me. Thank you for listening. So, any questions? You're not allowed to, Michael. You talk too much already.
Hiya. Is this a result of conscious user actions that so many users that are there now, or is it some kind of operating system update, Android or similar?
I'm quite convinced it's somebody who's put this in as a default.
Do you know what's in?
Nope. I have no clue at all who these people are.
Okay.
Traffic started increasing. Nobody has mailed me, said anything. I haven't seen anything on the NTP mailing lists. I might have missed it, but I have no clue who these people are.
Okay.
But I guess some router manufacturer, some operating system, somebody who builds a device doing something, put it in as a default, and they started rolling it out mid-October, and then they probably increased to 100,000 devices, thought, okay, this seems to work well, increase it a bit more, and now I mean, when I looked at this, I saw at least 5 million unique IP addresses. 20% of those were IPv6, 80% were IPv4. So some of those are sort of probably the same machine using both IPv4 and IPv6, but we're talking at least 5 million unique IP addresses, so 5 million unique devices.
Yep. Okay, thank you.
Spread across the world. The map is kind of boring, though, because if you look at the map, it's basically the same. If you Google for map over internet users in the world, it basically looks the same. So there's nothing really amazing about it. So in a way, I think for you who do networking professionally, which I do not, this is no surprise. It's nothing really big, but for me it is. Anybody else?
A quick question.
Yeah.
Here.
Oh, sorry.
When you were using Python,
Yeah.
did you use any common library?
Yes and no. It's Python 3, just basic Python 3. Yes, two major changes. We need HESSIV, which is a mode of AES. So it's a custom mode. It's an what do you call it? It's a mode which does both authentication and encryption. So you can say encrypt this packet with a bit of additional data that you sign. So AES-SIV is not part of the standard Python libraries or not part of OpenSSL either, I believe. So we have a custom implementation of that. One of the guys who did one of the first drafts for NTS is Daniel Franke, and he did a C library. And I've been using, I think he actually did a Python plugin for it, so I'm using that code. And the second part is that there's a part of TLS which is called export key material, where you say you have a running TLS session, and from that one both sides can get a shared secret somehow. And that API is not available in Python, and I had to hack that into Python. And unfortunately, they don't want to take a patch to add it to the standard Python OpenSSL libraries, so I have to basically maintain my own branch of Python to keep that small patch in, because it has to poke at the internals of the OpenSSL library. I'm trying to get away from that, but I haven't got a good solution yet, but I'll keep looking at it.
Yeah. First, a quick question. Will the slides be published somewhere?
Yeah, I think so.
Okay.
Yes.
And then, do you know, like, you said that most Linux things already support NTS. Do you know if other platforms support it? And then also, I have a second question that's also basically the same.
Yeah.
Netnod does this NTS. Do you know, like, how many other places that is read NTP also do NTS?
Well, since NTP and Crony do NTS, you can basically, if you have your own NTP server running on Linux today, well, you can set up your own NTS server. I do believe Cloudflare still does NTS on their time servers, but I know that somebody from Cloudflare was involved in NTS, Watson Ladd, in the beginning. I think he has left Cloudflare now, and I don't know if that was ever a sort of a officially supported service. But I believe they still do. Have to check, actually. Was your question sort of where can you run NTS? Or the thing, since you have an NTP and Crony, they can run on Linux. There is the first implementation of NTS from Martin Langer did run on Windows. It should be possible to make it run again, but I don't think it's been kept up to date. And you might be able to run NTPsec or Crony in Windows subsystem for Linux, since it's basically Linux. I don't know if you have the right permission to set the system clock from Linux, though. So if you want to try it, please do. And since Mac OS is just Unix, well, you should be able to run NTPsec and Crony on Mac OS. But I'm not a Mac person. I don't actually own one. So I threw the one I got away before I ever used it. So don't know, but it should be possible to make it run on most operating systems that do TLS.
So it's basically just Netnod and Cloudflare that have the NTS servers?
Publicly available NTS servers, correct, yes.
Okay, thanks.
I'm going to paraphrase this question a little bit, but basically someone is wondering what you're expecting in the future for NTS? What's going to happen next?
Well, I hope for adoption. I would love if Microsoft put NTS into Windows. There are NTP clients in Microsoft servers. It would be nice if they did put NTS in there. I know that systemd there was a patch for systemd to add NTS support. I don't think that patch was ever merged. I made a few comments on the pull request that they messed something up and they fixed that, but I don't think that ever got merged into mainline. A company that you might know about, Axis, who do network cameras, they actually do NTS. They support NTS today in their cameras. But you have to first, we actually believe that the users here might have been Axis, because I kind of believe that if Axis turned on NTS by default in their cameras, you'd see this kind of usage. But we talked to them, and they say that they have support for it, but users have to turn it on. And so I do not believe that it's their users who do this. But basically, yeah, I hope everybody starts using it.
I mean, the whole world, I don't think, should use the Netnod NTS servers. So how many more are deploying new servers?
I mean, on the thing is that all of this traffic to the NTSK servers ends up being a few kilobits to our timestamping servers. And we can handle 10 gigabits on our timestamping servers. And the basic idea is that phase one, do the key exchange. You do that once. And then you can just keep using your cookies that you get. You can use them forever. So basically, if people do a correct implementation of an NTS client where they do 1 KE connection, which we can scale up by adding more servers, we can handle the world, almost handle the world with NTP traffic.
Understood that. I just don't think that's still a good idea for resiliency reason. If they lose connectivity to Sweden, then they can't do
Okay,
NTS
yeah,
anymore.
that's a problem. So
I mean, it would be nice if there were more servers around. So have you heard about anyone else who's getting the FPGA code and setting all this up? Okay.
There are some more vendors, P2B, Germany, Time.nl, Netherlands, that have public NTS servers.
Yeah.
System 76, I don't know what it is.
I think some of those might actually be test implementations. And
they say they are in production here on the GitHub list.
And they're saying that anybody can use them, or?
Yeah,
Okay.
my question is, are they the FPGA-based variant, so they actually have some performance?
I'd say no. Or I don't know if anybody has downloaded our code from GitHub, because, well, it's all on GitHub. So if you have a VC709 or VC118 reference card from Xilinx, you can basically download everything and run it. So the code is totally open for anybody.
Okay.
Any other questions?
Thank you, Christer.
So 10 minutes early, you're free to go. Thank you.